Hello world, my name is Victor Engelmann. Welcome back to this video series on building a professional grade network using Linux. In this video I want to talk about the domain name system, DNS. Now what does DNS do? Well, a domain name is something like the name of some server, like when you go to facebook.com or google.com or amazon.com or any other web page, wikipedia.org, whatever, that name is the domain name of that website, okay? And you cannot connect to a domain name directly. You establish a IPv6 connection or maybe IPv4, but the point is you have this low-level TCP/IP or TCP/IPv6 connection, which doesn't use this name in any way. It uses an IPv4 address or an IPv6 address, but not that name itself, okay? So there has to be some way to translate this name, google.com for example, to this IPv4 address or this IPv6 address. And that is what the DNS domain name system does. That's very much like a phone book, if you will. You have these names and the corresponding addresses instead of phone numbers. And that's very much how this works, except that DNS is a distributed database, which means that there are a lot of DNS servers involved in the connection to some website, because no central DNS server has all these entries. Okay, it would be too much, and it would also be too much traffic for this central DNS server. Okay, so a DNS request looks like this. You have this root zone dot, and then below that you get this tree-like structure with the top-level domains like .com or .org or .de and all these other top-level domains. Okay, and then below that you have something like .facebook.com and .wikipedia.org. And technically this is actually wrong. So technically there has to be a dot at the end of this also for this root dot, but nobody uses that actually anymore, but technically it has to be there. These the servers for these domains then can have subdomains like, I don't know, de.wikipedia.org and en.wikipedia.org and so on. And normally when we are talking about websites, then you would have something like www.facebook.com and maybe something like, I don't know, VPN for their internal stuff, vpn.facebook.com or something like that. Okay. So, domain names form this tree-like structure. And what happens now when you try to access one of these domains is you have these root DNS servers. Okay. And when your computer now tries to access, for example, en.wikipedia.org, what happens is it will send a request because of this final dot here to the root DNS server, and will ask the root DNS server, hey, who is en.wikipedia.org. Okay, but yeah, the root DNS server doesn't have all these addresses. Okay, it would be too much and too much traffic and stuff like that, and that's not what the root DNS is for. Okay, the root DNS will just look at the end of the address and say, well, I don't know where wikipedia.org is, but I know a DNS server for .org, for the .org zone. So that's the next database that you are talking to. So the root DNS will say, I don't know where that is, but ask this DNS server here. Okay, and then your computer will talk to this DNS server and say, hey, who is en.wikipedia.org? And this DNS server with .org will then say, I don't know en.wikipedia.org, but I know wikipedia.org. Which is the next database. Okay, and this is then already something controlled by the Wikimedia Foundation. So this server will then redirect you and tell you, I don't know en.wikipedia.org, but I know wikipedia.org, so talk to this server here. Okay, so then your computer will ask the wikipedia.org DNS server, hey, who is en.wikipedia.org? And yeah, this server should then have an entry in its database which says en is this address, some address here. Okay, and then this DNS server gives you that address, and then your computer can establish a connection to that address that you've gotten there. Okay. Now, this system is also at work inside your own network, even in your small little home network, okay? Your typical home router contains a little DNS server. And when you connect to some address from your computer, okay, so when your computer tries to resolve a URL here, then it will send a DNS request to your router. And yeah, either your router can do the same thing and redirect you to the root DNS servers, but that would be not really a typical thing to do. The DNS server on in your local networks will typically do what you call a recursive DNS request. Which means that the router will then go through this process of resolving a URL, and then when it has gotten the response, then it will give the response back to you. Okay. This process here, where you are redirected from server to server to server, that's called an iterative DNS request. Okay. But yeah, as I said, inside your local networks, you should normally have a recursive DNS. But one thing I want to point out is, if you have a DNS server that is connected to the internet, so it's reachable from the internet, then you shouldn't configure it to do recursive DNS, because, well, if you configure it to do recursive DNS and be accessible from the internet, then what can happen is some malicious people could send a request to your router and ask for a huge database entry from up here, but spoof the source address. So they might give you a different source address and say, hey, I want the entry for enwikipedia.org, but yeah, I'm actually one of the Google servers or something. Okay, so they might give you an IP address of some other machine out there as the source address, which then means that your router or your DNS server that has gotten a lot of data from this distributed database here will then send a lot of data to that victim. Okay, so your DNS server then is participating in a so-called DNS amplification attack. Okay, that's just something to keep in mind. Don't do recursive DNS if you have a public DNS server. Okay. Okay, so let's build a DNS server. As you can see, everything is the way it was at the end of the last video. Okay, I'm in VLAN 4 here with a 24 net mask. 10.1.4.10 is the IP address, and yeah, the net core at 10.1.4.254 is the gateway. And currently I'm using the Google DNS server for domain resolution. This is what I'm going to change today. And over here you can see that yeah, things are almost exactly as before. So port 1 and 4 are trunking ports. Port 1 goes to the other switch, port 4 goes to the net core. Then port 3 is where I have connected my laptop. So this is in VLAN 4. And something that I've prepared since last time is I have moved port 6 into VLAN 2. You see, port 6, VLAN 2. And yeah, that's the net test, the Raspberry on which I want to install the DNS server today. So yeah, I've given the Raspberry a static IP address in the meantime, so we can now connect to it. I've given it the IP address 10.1.2 because it's in VLAN 2, 100. Okay. So now I'm connected to the Raspberry, and yeah, I've configured the static IP address using this DHCP CD configuration file. Here's the IP address, net mask, the static router, the net core, and I've given it my Fritzbox as domain name server for now because yeah, I need to install some software, and for that the Raspberry needs to be able to find the package sources. And yeah, for that it needs to be able to resolve deb.debian.org, for example. And yeah, so it needs a working DNS server to be able to do that. Ironic, I know, but if all else fails, you could resolve these addresses somewhere else and then put the addresses into the hosts file of the Raspberry if you really don't have a DNS server in your network. Okay, so I want to install the DNS server now, but every video out there that shows you how to do anything with Linux, they always tell you to update your package sources and install updates first, right? And I often skip this step because yeah, it's usually not that important, but this time it's really, really, really important that you are up to date. So I'm going to update the package sources, and well, maybe you don't need to install all the updates, but at least the package sources need to be need to be up to date, because if they are outdated, you might get outdated encryption keys for the connection to the root servers. And yeah, if that happens, yeah, the DNS server will not work, and I haven't even found a way to get it to work after that, other than completely uninstalling it and really deleting all the configurations and really starting over. So do yourself a favor, and in this case really update first. Okay, and yeah, just to be sure, I will reboot the Raspberry. Okay, so now let's install the packages that we need for the DNS server. We need bind 9 utils, and bind 9-doc. Okay, so let's see. So the server is already running, and yeah, with the default configuration, it just works as a forwarding DNS server. So I'll open another tab here. So now from my laptop, I will ask it for the IP address of, let's say, google.com 10.1.2.100. So with the command host, you can resolve a host name. I'm resolving the host name google.com using the server, my Raspberry 10.1.2.100. Okay, it refuses access. I'm guessing this is because I'm on a different VLAN. So I'm outside of its subnet. Okay, so let's address that first. In etc bind you have this namedconf, which just includes these other configuration files, and yeah, options and local are really the ones that we need. So now to allow IP addresses outside of its own subnet range to query host names, we will need to put a configuration here, allow query, and then in these curly braces we will define who is going to be allowed to query. I could now put IP addresses here like 10.1.4.0.24, or you can put multiple in there by separating them with semicolons, but I think a better way to do this is to use IP range groups. They are called ACLs here. So we will define an ACL called trusted, and I will put 10.1.00/16 in here. Although if you want this to be usable, maybe if you want this to be also a fallback DNS server for other sites, in case their DNS servers crash or something, You might even put the entire 10.everything range in here, but anyhow. So, and there needs to be a semicolon at the end here also. So now I have this ACL and I will put it in here like this. Okay, so now everyone with a 10 at the beginning of the IP address will be allowed to query. Okay, exit. Restart bind to apply the configuration. Let's see what happens now. Okay, it seems it had some problems. Okay, I think we need to set up these forwarders here. So here we could put 8888, but I would prefer to put my Fritzbox also in here, because my Fritzbox also does caching, and using this local cache should get us better performance. But I would still put 8888 here as a fallback option in case, yeah, maybe the Fritzbox breaks, or I mean, if the Fritzbox breaks, then I probably won't have internet access in the first place, but let's see what happens now. Okay, now we get a response. But at this point, yeah, the Raspberry doesn't do very much. When I ask it who is google.com, it basically just says, I don't know, ask the Fritzbox. Okay, and then the laptop asks the Fritzbox, but the Raspberry doesn't do anything. Okay, so what I will do now instead is I will tell it to do recursion. Recursion, yes. So when I then ask the Raspberry who is google.com, then, well, okay, then it will ask the Fritzbox, which is still not doing very much, but anyhow. As I've told you, when you turn on recursion, your DNS server should not be publicly accessible, because it would then be able to be used for DNS amplification attacks. And yeah, therefore, to prevent this from happening ever, even if we accidentally expose this Raspberry on the internet ever, I would also set allow recursion only for the trusted IP range. Okay, so I'm using the ACL here again. Okay, so only local IP addresses will be allowed to do recursive queries. I mean, if we want to expose this thing on the internet without recursion, we could put any here, so anybody could ask us about entries in our own database, but I will keep this untrusted for now. Okay. Apply the configuration. Okay, now I've asked it for the location of google.com again, and I think the time it took was much quicker this time. Yeah, but one thing I'm already seeing here is we are getting an IPv6 address, okay, and that can be a problem, because we are only running IPv4 on our network right now, and if the DNS server now tries to do anything with IPv6, then things might time out and fail, and you will get a lot of log messages in some log files on the Raspberry, and they might just clutter your hard drive, and I don't know, it might even make your DNS server fail sometime in the future. So to stop that from happening, I will go to etc default named and set this environment variable for the process to -4 additionally, so that it only uses IPv4. Okay, so we don't get the error messages related to IPv6 in our log files. Okay. Okay, we are still getting IPv6 addresses, but anyhow. Okay, but at this point the Raspberry still doesn't do very much, because when I ask it for the address of some host name, it still doesn't really answer the question. It just forwards the question to a different server and then forwards the answer back to us, right? And I mean, it makes sense that it does that, because always remember, DNS is really just a distributed database, okay? And yeah, it totally makes sense that this Raspberry doesn't do anything yet, because yeah, it is not responsible for any entry in that distributed database, okay? So it totally makes sense that it doesn't do anything. So yeah, that's what we will do now. We will give it entries that it is responsible for. And to do that, we will now edit the other config file, named local. And in here we define our zones. A zone really is a domain name and every subdomain under that, okay? So we might define the zone engelmann.local, for example. And then we have to describe that zone. Zones always need to have a type, and if this Raspberry is responsible for this zone, then we need to set the type master. And we have to specify a file, a so-called zone file. If you Google anything with DNS, Googling for zone file is very helpful. Okay, I will put here etc bind zones db.engelmann.local. Save and exit. Okay, and now I will create that directory. Okay, nothing in here yet. I will copy a file from etc bind. I will take db local and put it here as just as a starting point. Okay, now this is a so-called zone file, and for our purposes this is complete nonsense what we have here, but as a starting point, I think it's at least good to see something. What a zone file does is, it's basically a little database, right? You have these columns here, 4 columns basically, and what they mean is the first column is a name that you can query. The second column is for the protocol, and yeah, today basically we are only using IP networks anymore, so you will hardly find any network where you have any entry that is not IN here, which stands for internet. So this means internet protocol, so an IP protocol. And then the third column is for the type of the entry in that database. And the fourth column is the data of that entry. Okay. So for example, we have here an add. An add is just a shorthand for the add is a shorthand for this origin of the zone. So this name here is going to be replaced for this add. So this is really the same as if you had engelmann.local here, but anyhow. And yeah, this is what you see here now. Engelmann.local IP authoritative answer is 127.0.0.1. AAAA answers are for IPv6. And yeah, this basically does the same thing as this line, just for IPv6. So : 1 is the loopback interface in IPv6. But yeah, these entries are really not very helpful. These are for the loopback interface, as you can see up here. If I want to talk to engelmann.local from my laptop and I'm asking the Raspberry and it tells me 127.0.0.1 is engelmann.local, yeah, then if I'm trying to communicate with engelmann.local, then my laptop will try to talk to itself, because from its point of view, 127.0.0.1 is itself. Okay, so these entries here really make no sense outside of a loopback interface. So let's replace them with something else, like I will put the Fritz box in here with 192, 168, 178.1. Yeah, the name server of this domain is the Raspberry, so I will put ns.engelmann.local here. So this says if you're looking for the name server, yeah, this ns here stands for name server, you need to go to ns.engelmann.local, and now we can define who that is. ns IP protocol authoritative answer is 10.1.2.100, so the Raspberry. Okay, good. It would also be quite customary to give them numbers like ns1, because you might have multiple name servers. So you would name them ns1, ns2, and so on. Okay, now let's talk about this first entry here. This first line and also these following lines, they together are one entry of type SOA, which stands for start of authority. So the start of authority for engelmann.local is this host. Now localhost is wrong here again, because we are not doing the loopback interface. The primary name server for this zone is ns1.engelmann.local. Okay. Now this second address here, I personally don't like that very much. This is supposed to be the email address of the administrator of the server, but so you could do something like admin@engelmann.local, for example. Don't forget the trailing period. But yeah, the @ sign has a special meaning already, right here in the front. So instead of an @ you would put another period sign here, and now you have the problem that it is legal to have period signs on the left and on the right of your @ sign, So you could have something like admin.victor, for example, at engelmann.local. And now if you replace the at with a dot, it's not really clear which of these dots stands for the at sign. Okay, and you solve that by just escaping all the dots in the address part on the left of the at sign, and the first non-escaped period sign is the one that is supposed to correspond to the at sign. Yeah, I find that more complicated than it has any right to be, but okay. Now let's talk about the other numbers here. The serial, that's a very important number. Every time you change something in your zone file, you need to increase this serial number here, because this is used in the communication between primary and secondary servers. So when you have a mirror of your DNS server, then the mirror will regularly ask your primary server, hey, what's your serial number? And if the serial number hasn't changed or even decreased, then the mirror will say, oh, I have already a newer version or the same version of the file. I'm not going to synchronize. Okay. So if you make any changes here and don't increase the serial number, then your mirrors will not synchronize. Okay. So it is quite customary to use the current date for this. So 2022 07/11. Okay. So the date in ISO format, and then 2 characters for the revision of that day. Okay. So this might be today's first version of this file. And if I change it, I would change this to 2, 3, and so on. And if I make a change tomorrow, then I would change this to 12 and start with 1 here on the right again. Okay? Good. Now the refresh number specifies how often your secondary DNS mirrors should synchronize with your primary server. And yeah, I think this is for 1 day. I think 1 day is a bit much. I will set this to 1 hour. Okay, 3,600 seconds are 1 hour. The retry number here specifies what happens if your primary server goes down. Your secondary server tries to synchronize, but it cannot reach the primary one. Then it will wait for this many seconds and try again. Okay, and again, this is quite a lot. I will change this to maybe 10 minutes. So if the secondary server cannot reach the primary server, it will wait for 10 minutes and then try again. I think 10 minutes is a good number for this. Now this expire number here specifies basically how often your DNS mirrors will try to synchronize. Okay, so if you cannot synchronize, try again, try again, try again. But after this time, give up. Okay, if you couldn't synchronize for, I think this is 4 weeks, then just assume the zone just doesn't exist anymore. I think you can then delete it, or I don't know what it does, but that's what this number specifies. I think 4 weeks is a bit much. Let's take one day. Let's take 2 weeks. Okay. I think 2 weeks is really a good time because, well, if it's just 1 week, well, if your server goes down and maybe you have trouble getting replacement parts or something, then a repair might take longer than 1 week. So I think 1 week would be too short. I think 2 weeks is a good compromise. Okay. Now, negative cache TTL is a bit hard to explain. I think it's easier to understand if I first explain what TTL does up here. So if you, for example, access google.com, you get an address from your DNS server, and then you access google.com again, then your machine will not ask the DNS server again for an address. It will just reuse the address that the DNS server gave it before. Okay, and yeah, but at some point you still want your machine to update the information because it can change over time, right? And with this TTL, you control how long a machine is allowed to reuse an address after querying it. Okay, so I think it makes sense to set this to the same number as the refresh interval, so that your clients and your mirror servers agree about how long an address is valid, okay, before you have to update it. And by the way, this is just the default value. You can change that value individually for all records here. You can just add another column here and let's say this value changes so often that you are only allowed to reuse it for 30 seconds or something like that. Okay, so yeah. Now that is the normal TTL. The negative cache TTL down here now does kind of the opposite of TTL. You see, you can query addresses that don't exist, okay? And then the server will say that doesn't exist. And your machine will also cache that information, okay? It will then remember, okay, that address doesn't exist. So if you try to access it again, it will also reuse the information, hey, that address doesn't exist, okay? It's not going to ask the DNS server again. So you can query an address that doesn't exist, get a negative answer. Then you put that address into the DNS server, you try to access it again, but your machine will still say that address doesn't exist because it takes that information from its cache. Okay, it says, hey, I've just asked that 30 seconds ago and the DNS server said that doesn't exist. That's called an NX domain response, by the way. And yeah, this number here controls how long a machine will remember that an address didn't exist after it has gotten an NX domain response. Okay, so so it's kind of also a TTL, but for the negative answers, if that makes sense. Yeah. I'll set this to 1 hour also. Okay, this is looking pretty good. So let's try this. Okay, we are still getting responses for google.com. That is a good sign. Now let's ask it for name server1.engelmann.local. And we are getting a response 10.1.2.100. And who is fritz.engelmann.local? 192, 168, 178.1. Yeah, this is good. Okay, now there are lots of other kinds of record types. Okay, we've talked about ZOA, NS, A, and 4As. But there's really a lot of other kinds. So if you Google for record types, you will find a lot of record types here. Here we have A, and a lot of others. I want to point out CNAME, which is a very important one. This is for, basically for redirecting. There's also pointer, that's important. This one is similar to CNAME, but with a CNAME you basically start the resolving over with the new name that you've gotten, and pointer stops there. TXT is just some raw text that you can get, but I think these are already the most important ones that we've already talked about. So let's continue. And now let's talk about doing a mirror. So right now we have one zone. We could put more zones in there, right? But right now we only have one. Let's say we have a company and we merge with a different company, or one of the companies buys the other. Anyhow, we now have two separate companies. They both have their own DNS servers. They both have their own zones. Like we have engelmann.local, they have something.local. Then we might decide to say, hey, now we have two DNS servers at our hands. Let's use them as mirrors of each other. Okay, both of these servers stay the primary server for their own domains, but become mirrors of the other. Okay, that's something interesting you can do in the DNS world. So servers are not primary servers or secondary servers per se. Okay, they can be primary for some zones and secondary for other zones. So the other company is something.local. Again, we need to set a type. And if we make a copy of their entries, then we need to set the type slave. Now this terminology is not politically correct anymore, but it's still the terminology that is used in BIND. So then we need to specify a file, just like up here, except that we don't have to write the file ourselves. Or we might put them in a different subdirectory. Okay. And then we have to specify who is the master server. And let's say the other site has 10.2. Okay, they also have their infrastructure in VLAN 2, so we would have a private IP address, site 2, VLAN 2, number 100, for example. Okay, so like this we can specify that we want to make a copy of this zone under this file, and we want to get it from this primary server. Okay, so now we make a copy of their database and they want to make a copy of our database. Okay, right now I don't think this is allowed by default, so for this we have allow transfer. Here in the global options, I think I would tend to set this to none. So by default, nothing is allowed to be copied. None is just an automatically generated ACL, which just has no entries. There's also an ACL any, which contains an entry for 0000/0. So that will accept everything. But yeah. So allow transfer none says that by default we don't allow anybody to make a copy of our database. And yeah, now we can set an ACL that I would name DNS servers. And here I would put 10.1.2.100, so my own server, but also 10.2.2.100, so the something.local name server. Okay. So now we could say DNS servers are generally allowed to make copies of all our zones, but yeah, this is again a matter of taste or how strict you want to be. I will set it here to none, and then here you can say allow transfer DNS servers, so the ACL that we've just created. Okay, so this now says that this zone is allowed to be copied, and yeah, so like this we can now control per zone who is allowed to make copies. I mean, yeah, this is a bit paranoid, I admit that. I think it would also be completely fine to globally allow all DNS servers to make copies of all your zones, but yeah, you can do it like this, and yeah. Now, if you have this secondary name server in this other company that mirrors your name server, then it would make sense to also tell your network that this is a mirror of your DNS server. So you can go to your zone file, and in here you can now say, for my domain, for the IP protocol, I have a name server, maybe ns1.something.local. Okay, so here we are now saying that their primary name server, assuming that it's also called ns1, like our name server, is also a name server for our zone. Okay, so this NS record says this is also a legal server to ask about our engelmann.local names. And unlike our own name server here, we don't even have to put this in here, like ns1.something.local, for example. We don't have to put that here because something.local is not inside our own zone. Okay, if someone wants to talk, or if someone wants to query about our zone using this server, then they will resolve something.local. That's not our business. Okay, we don't have to take care of that. Okay, so if they decide to use their server, yeah, then they have to talk to their server and ask them who is ns1.something.local. Okay, we don't need to know that. They know it, and we have already redirected the clients to use that server. But let's say you've merged with a different company. Let's say you want to tell your clients about the machines in the other network, okay, so that they can address them with their name, I don't know, SQL server 1.something.local, so something in their network, which is controlled by their DNS server, but you don't want to make a copy of their database locally for whatever reason. Maybe they are too paranoid and they don't want to allow transfer or whatever. You can also create a zone, something 2.local with type forward. And set it to forward only. And then define as forwarder maybe 10.2.2.100. So like this, you will not make a local copy of their database. You just make this this zone something 2.local known inside your own network. Okay, so that your machines can ask about domain names from their network, because yeah, I mean, .local domains are not public. You wouldn't be able to get this from your backend DNS servers like 8888 or your Fritzbox or whatever. So here you explicitly tell it, if you want to ask about any something 2.local address, you have to forward this to this DNS server. Okay, now I will comment this out, because these are not real zones. Okay, now let's talk about reverse lookup zones. And yeah, I have to say, I'm not a huge fan of the way reverse lookup zones are solved, because yeah, this really shows the shortcoming of the DNS system. You know, it really shows that DNS in the end is really just a distributed database, and the way this reverse lookup is implemented, yeah, really is just a hack to make your DNS server give answers to this question, but it's really not elegant. So the way you do that is you define a zone named in-adder.arpa. And then you put your IP address in front of that, but in reverse order. So we would put 10.1 here, okay. Type master, file. And then I would name it something like db.10.1, for example. And allow transfer. Okay. So you see, when you try to reverse lookup an IP address, what your computer really does is it asks the DNS server for your IP address in reverse order .in-adder.arpa. Okay, so now we create a zone with the start of your IP address, and then put the rest of your IP address as entries in that zone file. So for example, oops. Okay. And now in here I will set these values again. Okay, the primary server of this fake zone is ns1.engelmann.local. Admin is again admin okay. Now the name servers for this zone, for this fake zone, are ns1.engelmann.local. And again, I might set ns1.something.local for this also. But I will keep it out. And yeah, now the trick now is remember that we have a zone called 1.10.inother.arpa. Okay, and when someone tries to look up my IP address, it will ask the DNS server for my IP address, but in reverse order, so 10.4.1.10, right? 10 is private range, site 1, VLAN 4, address 10. That's my IP address of this machine. Dot in-other.arpa. Okay, if someone wants to reverse look up my IP address, then they will query the DNS server for this address, and then the DNS server will see, okay, this here is this zone, and the rest here, this 10.4, will be something, will be an entry in this database. So 10.4 is a pointer to laptop.engelmann.local, for example. Okay, and 100.2 would be in pointer ns1.engelmann.local. Okay, so you're really just splitting your IP address into a fake domain name under this in-other.arpa fake zone. Okay, and just the first 2 bytes, or you can decide how many bytes you want to put in the zone and how many you want to put in the column. But yeah, this is really just a fake DNS entry. Okay, so let's see if we now restart this server. Now let's check for I've forgotten a semicolon here. Okay, now it seems to be running again. Okay, now you see I've done a reverse lookup of this IP address, but what it really did was turn the IP address around. .inadder.arpa and received the pointer response, a PTR response of ns1.engelmann.local. And if I query for 10.1.4.10, I will find out that's the address of the laptop. Again, as I said, kind of an ugly hack, but okay, that's how reverse lookup works anyhow. Now the last topic I want to talk about are so-called views. Our netcore core switch is in all of our VLANs, right? And it has different IP addresses in all of these VLANs. So our DNS server really should return different IP addresses depending on who asks for the name netcore. Okay, so and you do that using a so-called view. So we will edit the named-conf local again. I will throw this out. Now I will basically make separate configurations for all VLANs. So I will create a so-called view. I will name it VLAN 3. Or let's start with VLAN 4, because that's the one that already has a client in it. And let's see, I think I will just name that for underscore and the old name. And here the same thing. And the important thing here now is that we put here match-clients. And here I will now put 10.1.4.0/24. Okay, so clients from VLAN 4 will get answers for VLAN 4. Now I could rename db.engelmann.local, but I want db.engelmann.local to be kind of like the common core for all the VLANs, and only add additional entries depending on the VLAN. You know, because the IP address of everything else is just fixed, right? The name server, for example, is always 10.1.2.100. It's just that the netcore has different IP addresses depending on the VLAN, right? So okay, and in here I will now create an entry for netcore, IN, authoritative answer 10.1.4.254, right? And with $include, I can now include the other file here. Okay, now let me do the same thing for the reverse lookup zone. But actually I don't think that it makes that much sense to have reverse lookups per VLAN, because yeah, whether or not an address is inside your VLAN doesn't change the fact that this address is still for that machine. So we might just put the 10.1.1, 254, 10.1.2, 254, 10.1.3, 254, and 10.1.4, 254 all in the same reverse lookup zone. So why bother, you know? So then you only have one reverse lookup zone. Okay, let's see. Not getting an answer again. Okay, I used named checkconf, which tells me that when using view statements, all zones must be in views. Okay. Is that not the case? Huh. This seems to be the problem here. Here we are including these default zones, and they weren't inside views, and okay, bind requires that all zones are in views. They weren't, so okay, fine. Okay, now it seems to be running. Okay, now try again. Host netcore.engelmann.local, and we ask 10.1 to 100. And yeah, as you can see, we now have an answer. Let's do a reverse lookup. 10.1.4 254, and we get netcore Engelmann local. And this view functionality is what you would also probably want to use if you want to make your DNS server publicly available. Okay, so if you go to a registrar and buy a domain, then you can register your DNS server as a name server for that domain that you've bought at a registrar. You would have to give it a publicly accessible IP address for the DNS server. And then on the DNS server, you could create a view, maybe call it public. Yeah, match clients, might be any. And in here, you might put a zone for your domain, whatever it's called, something.com. And in here, type master file, whatever, some zone file for it, where you would register your web servers, your mail servers, I don't know, your VPN servers, your FTP servers, SSH servers, whatever. You can do it with it what you want, and then you might want to forbid transfer, except, yeah, you can then allow list it, but whatever. And yeah, this is then how you could make a publicly accessible DNS server for a domain that is publicly routable through the internet, so that if somebody then accesses your something.com, then the registrar will have notified the servers of the top level domain that something.com goes to the IP address that you've given it, and yeah, then if someone accesses something.com, then their machine will start talking to your DNS server and ask, hey, who is www.something.com, for example. Okay. So the .com part would be resolved by the root server, then the something part of that would be resolved by the .com servers, and then that server would give your DNS server's IP address to the client, and then the client would ask your DNS server for the entry for www. Okay, I hope that makes sense. Okay, so we have a working DNS server. So what we can do now is we can put this DNS server in here as our DNS server for this connection. But I need to warn you, I've had problems here. So I'm using if I run systemd resolve status, it's telling me it's using 10.1.2.100 as a backend, right? So it has taken this setting here. But if I now try to resolve something like netcore.engelmann.local without a server, it should use this server now, right? But I'm not getting an answer. And the reason for this seems to be that I'm running Ubuntu, and Ubuntu runs a local DNS server in the background, and it uses that for the resolution, okay? And that intermediate server seems to strip away something.local addresses, so it asks just for netcore, and for netcore I'm getting the same server fail. Yeah, the way to resolve this is to set the search domain. Okay. Okay, and now if I query it, then I'm getting a response. And since engelmann.local is my search domain, I don't even need to put this .engelmann.local here. I can just query the host name without the domain name. I don't have to put the fully qualified domain name for things inside my primary search domain. Okay. Yeah. Okay, now the last topic I want to talk about is how you can block domains. And you can do that with a fake zone. So I can just put a zone here, let's say Microsoft.com, for example. Of type master, you give it a zone file. db blocked. Okay. And in here, I will basically just tell it that at in A goes to 127.0.0.1, or maybe let's redirect it to 192.168.178.1. And with star, yeah, star matches anything, so yeah, this header should work because we are using the Raspberry as domain server for this. And yeah, now we have, now we redirect everything .microsoft.com to the Fritzbox. Okay, zone Microsoft.com has no NS records. Okay, all zones loaded. This is looking good. So now let's try to access Microsoft.com. And yeah, I'm redirected to the Fritzbox. But okay, the Fritzbox has refused my my request due to DNS rebind protection. Anyhow, you see that I have now successfully redirected Microsoft.com. So so yeah, you could redirect this to some local file server that, or a local HTTP server that just displays this domain is blocked or something. But yeah, this is how you can deny list domains. Whew. Okay, that was a lot of work, but yeah, it's really an interesting topic. And yeah, if you like this video, like it, share it, subscribe, and see you next time.